Right now, as you sit here, you are floating inside a cavity blown open by ancient explosions. It stretches roughly 1,000 light-years across. Its walls are made of gas and dust compressed by the shockwaves of approximately 15 dead stars. Nearly every star-forming region within 500 light-years of you sits on the surface of this single structure. Scientists did not fully reconstruct it until 2022. Most people have never heard of it. It is called the local bubble, and our solar system drifted into it only about 5 million years ago, completely by accident. The space you think of as the calm, empty neighborhood around our sun is not calm, not empty, and not small. It is a massive scar left behind by ancient violence, and you are inside it right now. If you want to discover what the space around our solar system really looks like, and why it is nothing like what most people imagine, hit that like button and subscribe now. Get yourself comfortable. Let's begin. Most people, when they think about the space around our solar system, picture emptiness. A few scattered stars against a black background, maybe a vague sense of distance. They imagine our sun floating in a kind of neutral void, surrounded by nothing in particular for light years in every direction. This image is comfortable. It is also profoundly wrong. And to understand why, you have to start with the one thing that image leaves out completely. You have to understand what is supposed to be between the stars. Because interstellar space is not actually empty, not even close. The galaxy is filled with a substance called the interstellar medium. It is a vast, diffuse ocean of gas and dust that permeates the space between stellar systems. Most of it is hydrogen, some of it is helium, and a small fraction consists of heavier elements and microscopic dust grains. In the densest regions, this material clumps together into molecular clouds, massive structures where gravity eventually compresses gas into new stars. In thinner regions, it spreads out into a haze so faint that a cubic centimeter might contain only a single atom. This interstellar medium is not uniform. It has structure. It has texture. Some regions are hot and thin. Others are cold and dense. The medium is shaped by stellar winds, by radiation, and most dramatically by the explosions of dying stars. When a massive star reaches the end of its life and detonates as a supernova, the blast wave tears through the surrounding interstellar medium at thousands of kilometers per second, sweeping material outward and hollowing out enormous cavities. These cavities can persist for millions of years, slowly refilling as the surrounding gas and dust creep back inward. The local bubble is one of these cavities. It is a region where the interstellar medium has been largely cleared away, leaving behind a vast pocket of extremely low-density plasma, its displaced gas and dust swept outward into a dense shell of cold neutral hydrogen, compressed and piled up like snow, pushed to the edges of a cleared parking lot. Inside the bubble, the density of neutral hydrogen drops to roughly 100 times lower than the galactic average. In some directions, the density is closer to 1,000 times lower, where the typical interstellar medium might contain about 1 atom per cubic centimeter. The interior of the local bubble contains closer to 1 atom per 100 cubic centimeters. For all practical purposes, the bubble is a near vacuum compared to the space surrounding it. Every star you can see with your naked eye tonight is inside it. Every constellation you have ever learned sits within its boundaries. The familiar night sky is not a window onto the wider galaxy. It is a view from inside a cavern. But to feel the true shock of this, you have to understand just how small our solar system is compared to the structure it sits inside. Start with the sun. Everything you have ever known, every human civilization, every species that has ever lived, exists on a small rocky world orbiting a medium-sized star. Earth circles the sun at a distance of about 93 million miles, a measurement astronomers call 1 astronomical unit. That distance feels enormous by human standards. Light itself takes about 8 minutes to cross it. But in the context of the solar system, 1 astronomical unit is a short walk. Neptune, the outermost major planet, orbits at roughly 30 astronomical units from the Sun. Pluto, at its most distant point, reaches about 49 astronomical units. The Voyager 1 spacecraft, Launched in 1977 and still transmitting faint signals from the edge of our solar neighborhood, has traveled roughly 163 astronomical units from the Sun as of recent measurements. It is the most distant human-made object in existence. It has been flying outward for nearly 5 decades, and yet Voyager 1 has barely left the front porch. The Sun's gravitational influence extends vastly farther than the planet's. The Oort cloud, a theoretical shell of icy bodies that marks the outermost gravitational boundary of the solar system, is thought to extend out to roughly 100,000 astronomical units, possibly farther. At that distance, the Sun's gravity is so weak that passing stars can occasionally dislodge comets and send them tumbling inward on million-year journeys. The Oort cloud defines the true edge of the solar system in gravitational terms, and it stretches outward to about 1.5 light-years from the Sun. 1.5 light-years. That is the radius of everything we can meaningfully call ours. Now consider this. The local bubble spans roughly 1,000 light-years across. Its shell surface sits, on average, about 550 light-years from the Sun, though this distance varies wildly depending on the direction you look, ranging from as close as 230 light-years in some directions to well over 1,000 light-years in others. The bubble is not a perfect sphere. It is lumpy, irregular, and stretched. But even using the most conservative estimate of its extent, the local bubble is so much larger than the solar system that the comparison collapses into absurdity. If you shrank the solar system, including the full extent of the Oort cloud, down to the size of a single peppercorn, the local bubble surrounding it would be taller than you are. Your entire planetary system, every world, every moon, every asteroid, every comet drifting at the frozen edge of the Sun's gravitational reach would be a dark speck you could hold between 2 fingers. And the space around you, from floor to well above your head, would be the cavity of cleared-out interstellar gas in which that speck is embedded. That is not poetic exaggeration. That is close to the actual ratio. The local bubble is hundreds of times wider than the solar system's fullest gravitational extent. That is the first scale shock. The space most people think of as our cosmic neighborhood, the region around the Sun where the planets orbit and the nearest stars glimmer, is a microscopic speck, floating inside a structure so large it takes light a millennium to cross. We are not in open space. We are inside something. But the journey outward from the Sun does not jump straight to the bubble's walls. Between the solar system and the bubble's shell lies a layered series of structures that reveal how deeply embedded we really are. The first boundary you cross when leaving the solar system is the heliopause. This is the point where the solar wind, the constant stream of charged particles flowing outward from the Sun, finally loses its battle against the pressure of the surrounding interstellar medium. Inside the heliopause, the Sun's influence dominates. Outside it, interstellar space begins. Voyager 1 crossed this boundary in August of 2012, and Voyager 2 followed in November of 2018. Both spacecraft confirm that the transition is real, measurable, and dramatic. The density of particles, the direction of magnetic fields, and the energy of cosmic rays all changed abruptly as the probes passed through. Beyond the heliopause, our solar system is immersed in a small wisp of warm, partially ionized gas called the local interstellar cloud. This cloud is tiny by interstellar standards, roughly 30 light-years across, with a temperature of approximately 6,000 degrees Celsius and a density still far below the galactic average. It drifts through the local bubble at roughly 26 kilometers per second relative to our Sun. Scientists believe the solar system entered this cloud somewhere between 44,000 and 150,000 years ago, and we will likely exit it within the next 10,000 to 20,000 years, passing into a slightly different wisp of interstellar gas. The local interstellar cloud is not alone. It belongs to a family of similar small cloudlets collectively called the cluster of local interstellar clouds. These cloudlets are scattered throughout the interior of the local bubble like wisps of fog drifting through an enormous empty room. They are warm but sparse, partially ionized but not particularly dense. They represent the dregs of interstellar material that exist within the bubble's mostly evacuated interior. Their origin has been debated for decades, but many scientists now believe they are connected to the expanding shell of a neighboring superbubble, the Loop 1 superbubble, which has been pressing against the local bubble's boundary from the direction of the Scorpius-Centaurus stellar association. So here is the picture that begins to take shape. Our Sun is a single star. It sits inside a protective cocoon of solar wind called the heliosphere, which extends roughly 120 astronomical units outward in the direction of the Sun's motion through interstellar space. Beyond the heliosphere, we are immersed in a small interstellar cloud roughly 30 light-years across. That cloud is one of several cloudlets drifting inside the mostly empty interior of the local bubble, a cavity stretching roughly 1,000 light-years in diameter. And all of this, the Sun, the heliosphere, the cloud, the bubble, sits inside one arm of the Milky Way galaxy, which itself spans 100,000 light-years across. Each layer is enormously larger than the one before it, and each layer was invisible to human understanding until remarkably recently. The local bubble was first suspected in the 1970s, not through direct observation, but through indirect evidence. Astronomers studying soft X-ray emissions noticed something strange. The sky was glowing faintly in X-rays in a pattern that did not match the distribution of known stellar sources. The glow appeared to come from all around us, as though we were sitting inside a bath of extremely hot gas. The temperature implied by the X-ray spectrum was extraordinary, roughly 1 million degrees. That was far too hot to be explained by ordinary interstellar gas, but it was exactly what you would expect if the Sun were located inside a large, old supernova remnant, a cavity where ancient explosions had heated the interior gas to extreme temperatures and cleared away the denser material. Throughout the 1980s and 90s, additional evidence accumulated. Observations of nearby stars revealed an unusual pattern in interstellar absorption. Stars within a few hundred light-years showed very little absorption from cold neutral gas along the line of sight, indicating that the space between us and those stars was largely empty. Stars beyond a few hundred light-years showed significantly more absorption, suggesting a sudden increase in density at a specific distance. This was the wall of the bubble, the compressed shell of gas and dust surrounding the evacuated interior. Radio observations, ultraviolet surveys, and early three-dimensional dust maps all pointed toward the same conclusion. The Sun sits inside a large, low-density cavity, surrounded by a denser shell. The cavity has an irregular shape, narrower in the galactic plane and possibly open toward the galactic poles, and its origin, as scientists would eventually reconstruct, was violent. But the true breakthrough in understanding the local bubble came much more recently, and it relied on a spacecraft that was not even designed to study interstellar gas. The European Space Agency's Gaia mission, launched in 2013, was built to measure the precise positions, distances, and motions of over 1 billion stars in the Milky Way. Its primary goal was stellar cartography, not interstellar medium science. But the extraordinary precision of Gaia's data allowed researchers to do something that had never been possible before. They could build detailed three-dimensional maps of the dust and gas between the stars, not by observing the gas directly, but by measuring how it dimmed and reddened the light of background stars. By comparing how much each star's light had been altered by intervening dust, scientists could reconstruct the three-dimensional distribution of interstellar material with unprecedented resolution. The results were stunning. For the first time, astronomers could see the local bubble not as a vague theoretical concept, but as a specific three-dimensional structure with measurable walls, identifiable features, and a clear relationship to the surrounding interstellar landscape. The bubble's shell appeared in the dust maps as a distinct ring of higher density material surrounding the low-density interior where the Sun resides. Molecular clouds, the dense regions where new stars form, were clearly visible sitting on the bubble's surface like barnacles on the hull of a ship, and the Sun's position within the bubble turned out to be surprisingly central. Not exactly at the geometric center, but close enough to be remarkable. This was not because the bubble formed around us. It did not. The bubble was carved out by ancient supernovae that began exploding roughly 14 million years ago, long before the solar system was anywhere near this region. The Sun drifted into the bubble only about 5 million years ago, carried by its ordinary orbit around the galactic center. We are visitors inside this structure, not permanent residents. We happen to wander into a vast, ancient cavity, and we now sit near its middle purely by coincidence. This coincidence matters, because it shapes everything we observe. From our position near the center, the bubble's shell surrounds us in every direction. When we look out at the night sky, we are looking through the bubble's thin interior and, eventually, at or through its walls. The stars we see are overwhelmingly stars that also sit inside the bubble. The dust clouds we observe at moderate distances are sitting on the bubble's surface. The interstellar medium we study in our immediate vicinity has been processed, heated, and restructured by the same explosions that created the cavity we inhabit. We are not observing the galaxy from a neutral vantage point. We are observing it from inside a scar. To feel the weight of this, consider what the local bubble means for the most basic question in astronomy. How far away are the nearest star-forming regions? For decades, astronomers knew that several prominent molecular clouds, the birthplaces of new stars, lay within a few hundred light-years of the Sun. The Taurus molecular cloud, the Ophiuchus cloud complex, the Lupus clouds, the Chamaeleon clouds, the Corona Australis region. These are among the closest stellar nurseries to Earth, and they have been studied intensively for generations. What no one fully realized until the Gaia data made it visible was that all of these star-forming regions sit on the surface of the local bubble. Every single one. Not scattered randomly through space, not distributed evenly around the Sun. They are arranged on the bubble's shell, embedded in the compressed gas and dust that defines its boundary. A landmark study published in the journal Nature in January of 2022, led by astronomer Catherine Zucker at the Center for Astrophysics at Harvard and the Smithsonian, demonstrated this relationship using Gaia data and three-dimensional dust maps. The implications are enormous, and they depend on understanding how the bubble formed in the first place. Because if the bubble created the conditions for all nearby star formation, then the question of what carved this cavity is not just a question about interstellar gas. It is a question about the origin of every young star in our neighborhood. And the answer involves a chain of stellar deaths so violent and concentrated that their combined energy reshaped the interstellar medium across hundreds of light-years. This is not a minor detail. It means the entire nearby star-forming landscape, every young star within 500 light-years, is a direct consequence of the bubble's history. The structure we are inside is not a passive container. It is an active engine that shaped the stellar geography around us. And the Sun is sitting in the middle of it, watching the results unfold on every horizon. But how did this structure actually form? What sequence of events could hollow out a cavity 1,000 light-years across and pile its contents into walls dense enough to birth new stars? The answer involves a chain of stellar deaths so violent and concentrated that their combined energy reshaped the interstellar medium across hundreds of light-years. That chain, and the evidence scientists used to reconstruct it, is where everything truly begins to deepen. 14 million years ago, something began dying in a region of the Milky Way that our solar system had not yet reached. It was not one star, it was a sequence of them. A chain of massive, luminous stars, each one burning through its nuclear fuel with reckless speed, each one destined to collapse and explode within a few million years of its birth. These stars belong to a loose collection of young hot stars called an OB association, a group bound not tightly by gravity, but by a shared origin in the same giant molecular cloud. They were born together, scattered slowly apart, and died one by one over millions of years. This particular association is called Scorpius Centaurus. It is the nearest OB association to the Sun today, centered roughly 400 to 500 light-years away in the direction of the constellations Scorpius and Centaurus. It contains hundreds of young, massive stars organized into several subgroups, the most prominent being Upper Centaurus Lupus, Lower Centaurus Crux, and Upper Scorpius. These subgroups represent different generations of star formation within the association, each slightly younger than the last, each triggered in part by the deaths of stars from the generation before. Scorpius Centaurus is not a quiet stellar neighborhood. It is a factory of stellar violence. The most massive stars in an OB association, those with 10 or 20 or even 40 times the mass of our Sun, live fast and die catastrophically. A star with 20 solar masses might burn for only 8 to 10 million years before exhausting its fuel. When it does, its core collapses in less than a second, and the resulting supernova explosion releases more energy in a few weeks than our Sun will produce in its entire 10 billion year lifetime. The shock wave from a single supernova expands outward at thousands of kilometers per second, slamming into the surrounding interstellar medium like a wall of superheated plasma. It compresses, heats, and displaces the gas and dust in its path, carving out a bubble of hot, thin material that can persist for hundreds of thousands of years. A single supernova remnant might clear a cavity tens of light years across. But what happens when you get 15 of them in roughly the same region over the course of several million years? You do not get 15 separate bubbles. You get one enormous cavity, inflated by repeated injections of energy, each explosion expanding the walls outward a little farther, each shockwave reinforcing and re-energizing the expansion of the one before it. The cumulative effect is a structure far larger and more persistent than any individual supernova remnant could produce. Astronomers call these structures superbubbles, and the local bubble is one of them. The reconstruction of this violent history is one of the most remarkable achievements in recent interstellar science. For decades, astronomers suspected the local bubble had been carved by supernovae, but the details were fuzzy. How many explosions? When did they occur? Where were the stars that produced them? The answers required a combination of stellar archaeology, three-dimensional dust mapping, and isotopic evidence from the most unlikely of sources, the bottom of Earth's oceans. The first major piece of the puzzle came from tracing the motions of stars backward through time. Stars in the Milky Way do not sit still. They orbit the galactic center, and their positions change over millions of years. Using precise measurements of stellar positions and velocities from the Gaia spacecraft, researchers could rewind the clock and calculate where specific groups of young stars were located millions of years ago. This technique, called traceback analysis, revealed that the subgroups of the Scorpius-Centaurus association were positioned much closer to the current center of the local bubble in the deep past, roughly 14 million years ago. That timing was critical. It aligned with independent estimates of when the bubble began forming, based on the ages of the molecular clouds on its surface and the expansion rate of its shell. The match was not approximate. It was precise. The stars that could have produced the supernovae were in the right place at the right time to have created exactly the cavity we observe today. The traceback technique deserves a closer look, because it is one of the most remarkable pieces of detective work in modern astrophysics. And it almost did not work. The challenge is this: stars in the Milky Way do not sit still. They orbit the galactic center at speeds of roughly 220 kilometers per second, and their individual trajectories are further perturbed by the gravitational influence of spiral arms, molecular clouds, and neighboring stars. Over 14 million years, a star can travel thousands of light years from its birthplace. The stars that produced the supernovae responsible for the local bubble have long since scattered. The explosions destroyed the stars themselves, leaving behind neutron stars or black holes that are extraordinarily difficult to locate. The crime scene is 14 million years cold, the perpetrators are dead, and the witnesses have dispersed across a vast stretch of the galaxy. What researchers needed was a time machine. What they had was Gaia. The Gaia spacecraft measures not just the positions of stars but their velocities, both across the sky and along the line of sight. For nearby stars, these measurements are precise enough to calculate where each star was located millions of years ago, assuming you know how the galaxy's gravitational field affects trajectories over that timescale. This is not a simple extrapolation. It requires modeling the gravitational potential of the entire galactic disk, including the contributions of spiral arms, the central bar, and the dark matter halo, and then integrating each star's orbit backward through that potential. The researchers focused on the youngest stellar subgroups within the Scorpius-Centaurus association. These subgroups contain stars that form together and have not yet had time to disperse very far from their birthplace. By tracing the motions of these surviving stars backward, the team could estimate where the subgroup was located when its most massive members, the ones that would have become supernovae, were still alive. The results converged on a region near the geometric center of the present-day local bubble. 14 million years ago, the Upper Centaurus Lupus subgroup was concentrated in a volume of space that now lies deep inside the bubble's evacuated interior. The Lower Centaurus Crux subgroup was nearby, slightly offset but still well within the bubble's current boundaries. The positions matched, the timing matched. The number of massive stars expected to have formed in those subgroups, based on the statistical relationship between cluster mass and the number of high mass members, was consistent with approximately 15 supernovae over a span of several million years. This was not a vague statistical argument. It was a specific, testable reconstruction. The researchers could point to identified groups of surviving stars, trace their orbits backward to a specific time and place, count the expected number of supernovae based on the initial mass function of the clusters, and compare the predicted energy output to the observed size and expansion rate of the bubble. Every link in the chain held. The local bubble was not created by unknown explosions in an unspecified location. It was created by specific stars, in a specific association, at a specific time, and the surviving siblings of those dead stars are still observable today, scattered across the sky in precisely the positions that the traceback calculations predict. This level of forensic precision in reconstructing an event 14 million years in the past is extraordinary. It is the interstellar equivalent of solving a cold case by finding the relatives of the perpetrator and tracing their family tree back to the scene of the crime. The evidence is circumstantial in the legal sense, but overwhelming in the scientific sense. Catherine Zucker's 2022 study brought this picture into sharp focus. Her team used the latest Gaia data combined with new three-dimensional dust maps to model the expansion of the local bubble over its entire 14 million year history. They treated the bubble as an expanding shell driven by a sequence of supernova explosions originating in the Upper Centaurus Lupus and Lower Centaurus Crux subgroups. By modeling how such a shell would grow over time, sweeping up ambient interstellar gas and decelerating as it accumulated mass, they could predict where the shell should be today, how fast it should be expanding, and where young stars born on its surface should be located. The predictions matched the observations with extraordinary precision. The modelled shell lined up with the observed dust walls of the bubble. The predicted expansion velocity, roughly 6 7/10 kilometers per second, matched the measured motions of young stars on the bubble's surface. The ages of nearby stellar clusters, arranged chronologically along the shell, were consistent with a wave of star formation triggered sequentially as the expanding shell reached new regions of ambient gas and compressed them to the point of gravitational collapse. The total mass of gas swept up into the shell was estimated at approximately 1.4 million solar masses. That is an almost incomprehensible amount of material. To put it in proportion, our entire Sun, the object that dominates our planetary system and contains 99.8% of all the mass in it, would need to be multiplied 1.4 million times to match the mass of gas piled into the local bubble's walls. All of that material was originally spread throughout the volume that is now the bubble's empty interior. The supernovae pushed it outward, compacting it, reorganizing it, turning a diffuse medium into a structured shell. And that shell did not just sit there, it became fertile. As the expanding shell of compressed gas and dust grew denser, it crossed a critical threshold. The accumulated material became heavy enough for gravity to begin pulling it inward, counteracting the outward pressure of the expansion. Portions of the shell fragmented, collapsed, and formed dense molecular clouds, the cold, dark regions where new stars are born. This is the process astronomers call collect and collapse, and it is one of the primary mechanisms by which supernova explosions trigger the next generation of star formation. The result is visible today in every direction we look. The torus molecular cloud, sitting on the bubble's wall, roughly 430 light-years away. The Ophiuchus cloud complex, embedded in the shell near the boundary with the Scorpius-Centaurus association. The Lupus clouds, the Chamaeleon clouds, the Corona Australis region, the Musca filament. Every one of these well-studied star-forming regions lies on the surface of the local bubble, not near it, on it, embedded in the compressed gas of its expanding shell. Before Zucker's study, astronomers had treated these star-forming regions as essentially independent objects scattered through the solar neighborhood by chance. After the study, they were revealed as products of a single coherent process. The local bubble's expansion created the conditions for all nearby star formation. The molecular clouds are not random features. They are fragments of the bubble's wall, This means the young stars forming in these clouds right now, protostars still gathering mass from their parent gas, T Tauri stars flickering with the energy of gravitational contraction, are the direct descendants of the supernovae that hollowed out the space we live in. The same explosions that cleared our cavity compressed the material that is now giving birth to the next generation of stars on our doorstep. Destruction and creation, linked by the same expanding shockwave across 14 million years of galactic history. But the evidence for the bubble's supernova origin does not come only from stellar motions and dust maps. It comes from a source far closer to home and far more startling. In the late 1990s and early 2000s, geochemists analyzing deep-sea sediment cores from the Pacific Ocean floor made an unexpected discovery. They found elevated concentrations of a specific radioactive isotope, iron-60. Iron-60 is not produced in significant quantities by any ordinary geological or biological process on Earth. It is overwhelmingly produced in the cores of massive stars and ejected into space by supernova explosions. It has a half-life of approximately 2.6 million years, which means any iron-60 that existed when the Earth formed 4.5 billion years ago has long since decayed away. If you find fresh iron-60 in a geological layer, it did not come from Earth. It came from space. Specifically, it came from a nearby supernova whose debris rained down onto our planet. The deep-sea sediment record revealed two distinct peaks of iron-60 deposition. The more recent peak occurred roughly 2 to 3 million years ago. A second, broader signal appeared at roughly 6 to 7 million years ago. Both of these timings are consistent with supernovae occurring in the Scorpius-Centaurus association during the later stages of the local bubble's formation. The iron-60 did not arrive in a single burst. It accumulated over extended periods, suggesting multiple supernova events spread across millions of years, exactly the pattern expected from a sequence of massive stars dying one after another in the same stellar association. The iron-60 evidence was electrifying because it was completely independent of the astronomical observations. It did not rely on dust maps, stellar motions, or X-ray emissions. It relied on atoms, physical particles that travelled from exploding stars across interstellar space, entered our solar system, drifted down through Earth's atmosphere, and settled on the ocean floor, where they were preserved in layers of sediment for millions of years. The supernovae that carved the local bubble left their fingerprints in the mud at the bottom of our oceans. The physical journey of those iron-60 atoms is worth pausing to consider, because it connects the abstract violence of a supernova to something you can hold in your hand. It begins inside the core of a massive star, where temperatures exceed 3 billion degrees and pressures crush matter to densities found nowhere else in the ordinary universe. Under these extreme conditions, nuclear fusion reactions build progressively heavier elements, fusing lighter nuclei into heavier ones, in a sequence that climbs the periodic table from hydrogen to helium to carbon to oxygen and onward. Iron-60 is forged near the end of this chain, in the final stages of a massive star's life, when the core is burning silicon and producing a family of iron group isotopes as byproducts of increasingly desperate nuclear reactions. When the star's core collapses and the supernova detonates, the outer layers of the star are blasted outward at velocities reaching 10,000 kilometers per second or more. The iron-60 atoms, along with the rest of the ejected material, are launched into interstellar space as an expanding shell of superheated debris. This ejector slams into the surrounding interstellar medium, creating a shockwave that sweeps up gas and dust as it expands. Over thousands of years, the ejector decelerates, mixes with the swept-up interstellar material, and gradually disperses into the broader interstellar medium. The iron-60 atoms, now embedded in microscopic grains of interstellar dust or drifting as individual ions in the hot plasma, spread outward across light-years of space. They drift through the interstellar medium for millions of years, carried by the same flows and currents that shape the gas between the stars. Eventually, some of those atoms enter the solar system. They drift past the outer planets, past the inner planets, and into the neighbourhood of Earth. Some are captured by Earth's gravitational field and settle slowly through the atmosphere, a process that takes months or years for microscopic particles falling from interstellar space. They land on the surface, on oceans and continents alike, and are incorporated into sedimentary layers on the ocean floor, where they are buried and preserved by the steady accumulation of marine sediment. Millions of years later, a geochemist drills a core from the Pacific Ocean floor, slices it into thin layers, and runs isotopic analysis on each layer. The iron 60 signal appears as a subtle but unmistakable spike in concentration at a specific depth, corresponding to a specific time in Earth's geological history. The atom that was forged in a stellar core at 3 billion degrees, ejected at 10,000 kilometers per second, drifted across hundreds of light years of interstellar space, settled through Earth's atmosphere, and sank to the bottom of the ocean is now sitting in a laboratory, being measured by instruments that did not exist when the star that created it was still alive. That is the physical chain connecting a supernova 14 million years ago to a measurement in a 21st century laboratory. It is not a metaphor. It is not a theoretical inference. It is atoms, real, countable atoms that travelled from a dying star to the bottom of Earth's oceans. The local bubble left its signature not in the sky, but in the ground beneath our feet. Additional studies found similar iron 60 signals in lunar soil samples, in Antarctic snow, and in cosmic ray measurements, all consistent with relatively recent supernova activity in the solar neighbourhood. The convergence of evidence from astronomy, geochemistry, and particle physics created an unusually robust picture. The local bubble was carved by real, identifiable explosions. Those explosions left physical traces on Earth, and the timing, location, and number of events all match the predictions from stellar evolution models of the Scorpius-Centaurus Association. The bubble's shape tells its own story of violence. Unlike the clean, spherical cavities depicted in textbook diagrams, the real local bubble is jagged, asymmetric, and deeply irregular. Its shell surface sits at an average distance of roughly 170 parsecs from the Sun, which is about 550 light-years. But that average conceals enormous variation. In some directions, the shell is as close as 70 parsecs, roughly 230 light-years. In others, it extends beyond 600 parsecs, well over 1,000 light-years away. The bubble is not round. It is stretched, compressed, and distorted by the uneven density of the interstellar medium it expanded into, and by the gravitational influence of neighbouring structures. The most detailed three-dimensional model of the bubble's surface was published in 2024 by Theo O'Neill, Catherine Zucker, and their colleagues, using a high-resolution dust map constructed from Gaia data by Gordian Edenhofer and collaborators. This new map achieved parsecant-scale resolution, meaning it could trace the distribution of interstellar dust at scales of just a few light-years. The resulting model of the bubble's shell revealed features that no previous map had been able to capture. The shell turned out to be roughly 35 parsecs thick on average, about 115 light-years. It is not a smooth wall but a corrugated, clumpy barrier riddled with substructure. Dense molecular clouds sit embedded within it. Thin spots and gaps appear where the shell has been punctured or eroded. And in one direction, toward the galactic north, the shell appears to be missing entirely. This last feature was the most dramatic finding of the 2024 study. The researchers concluded that the local bubble is not actually a closed bubble at all. It is a chimney. The upper portion of the shell, extending more than 600 parsecs above the galactic midplane, appears to have burst open, creating a channel through which hot gas and material from the bubble's interior can flow upward into the lower halo of the Milky Way. The reclassification from bubble to chimney is not merely a change of label, it transforms what the structure means in the context of the galaxy as a whole. A closed bubble is a local feature. It contains its hot gas, holds its processed material, and eventually fades as the interior cools and the walls dissipate. Its effects are confined to the region it occupies. A chimney is something fundamentally different. A chimney is a conduit. It connects the dense, star-forming disk of the galaxy to the diffuse, extended halo above and below it. Material that flows through a chimney does not stay local. It rises hundreds or thousands of parsecs above the galactic midplane, carrying with it the energy, metals, and momentum injected by the supernovae that created the cavity in the first place. This upward flow feeds into a galactic-scale circulation pattern called the galactic fountain. In this model, hot gas rises out of the disk through chimneys and superbubble blowouts, climbs into the lower halo, cools radiatively as it rises, and eventually condenses into clouds that fall back down onto the disk at a different location. The process redistributes metals across the galaxy, mixing freshly synthesized heavy elements from supernova ejecta into regions far from the original explosion sites. It also regulates the pressure and energy budget of the interstellar medium, preventing the disk from accumulating too much thermal energy in any one location. The local bubble, reinterpreted as a chimney, is therefore not just a cavity in the solar neighborhood. It is an active participant in the Milky Way's internal circulation. The same supernovae that cleared the space around our solar system may have injected material into the galactic halo that has since rained back down onto the disk hundreds or thousands of light years away. The violence that shaped our local environment did not stay local. It contributed to the galaxy's large-scale metabolic processes, cycling material between the disk and the halo in a feedback loop that has been operating for billions of years across the entire Milky Way. Our solar system, then, sits not just inside a supernova remnant, but inside a vent in the galactic floor. We are positioned within a structure that is actively channeling processed interstellar material from the disk of the galaxy into its halo. The chimney is not a relic, it is functioning. This is not entirely surprising from a theoretical perspective. Simulations of superbubbles have long predicted that sufficiently energetic cavities should eventually breach the thin disk of the galaxy and vent their contents into the halo. The galactic disk is only a few hundred parsecs thick in our neighborhood. A superbubble expanding in all directions will reach the top and bottom edges of the disk before it runs out of energy in the horizontal plane. When it breaks through, the pressurized interior gas rushes upward through the opening like steam escaping from a cracked lid. The local chimney, as the open structure might more accurately be called, appears to extend at least 600 parsecs above the galactic midplane in the north. In the south, the shell extends about 270 parsecs below the midplane, and may also show signs of thinning or opening, though the evidence is less clear. The overall shape, narrow in the galactic plane and extended toward the poles, gives the structure an hourglass or funnel-like geometry. This chimney morphology has profound implications. It means the local bubble is not a sealed container holding its hot gas in place. It is actively leaking. Material processed by the supernovae that created the bubble, including hot plasma, metals forged in stellar cores, and energy from the explosions themselves, may be flowing upward out of the galactic disk and into the Milky Way's halo, contributing to a process called the galactic fountain. In this fountain model, hot gas rises out of the disk through chimneys and superbubble blowouts, cools as it rises, and eventually falls back down onto the disk at a different location, recycling material across the galaxy. Our solar system, then, is not just sitting inside a supernova-carved cavity. It is sitting inside a vent, a channel through which the galaxy processes and recirculates its interstellar material. The structure we inhabit is not just a local feature. It is connected to the large-scale circulation of gas within the entire Milky Way. The bubble's walls also tell us something about the relationship between destruction and architecture. The shell is not featureless. It contains identifiable molecular clouds, filaments, clumps, and voids. Some of these features correspond to well-known astronomical objects that have been studied for decades without anyone realizing they were all part of the same structure. The Taurus-Perseus region, the Ophiuchus clouds, the Aquila rift, these are all components of the bubble's shell, arranged around us like the walls of an enormous room. The shell also shows evidence of interaction with neighboring structures. In the direction of the Scorpius-Centaurus association, the bubble's wall is compressed and distorted, pushed inward by the pressure of the adjacent Loop 1 superbubble, which was carved by more recent stellar activity in the same association. In other directions, tunnels and thin spots in the shell may connect the local bubble to other nearby cavities, creating an interlocking network of superbubble structures that riddles the interstellar medium like holes in Swiss cheese. The total mass of dust traced in the shell, approximately 600,000 solar masses according to the 2024 model, represents only a fraction of the total shell mass. Dust makes up roughly 1% of the interstellar medium by mass. The remaining 99% is gas, mostly hydrogen and helium, which brings the total estimated shell mass back to the million-plus solar mass range consistent with earlier estimates. All of that material was once spread through the volume that is now the bubble's sparse interior. The supernovae relocated it, reorganized it, and compressed it into the walls we observe today. The shell is still expanding, though it has slowed considerably from its initial explosive velocity. Current measurements place the expansion speed at roughly 6 to 7 kilometers per second, far slower than the thousands of kilometers per second at which the original shockwaves propagated, but still measurable. At this rate, the bubble continues to grow, pushing its walls outward, compressing new material, and potentially triggering new rounds of star formation in regions that have not yet been reached by the expanding shell. But the expansion is decelerating. The shell has swept up so much mass that its own inertia is slowing it down. Eventually, within the next several million years, the expansion will stall entirely. The shell will stop growing, and the bubble will begin the long, slow process of refilling as surrounding gas creeps back inward. Over tens of millions of years, the cavity will gradually close, the shell will disperse, and the local bubble will fade from the interstellar landscape. Unless, of course, new supernovae go off inside it before then, and given that the Scorpius-Centaurus association still contains massive stars that have not yet reached the end of their lives, that possibility is not remote. The bubble that exists today may be re-energized by future explosions, extending its lifetime and expanding its walls even farther. The history of the local bubble is not a single event, it is an ongoing process. A chain of stellar births and deaths stretching across 14 million years, reshaping the interstellar medium on scales of hundreds of light years, compressing gas into new star-forming clouds, and leaving behind a cavity so large that our entire solar system is a negligible speck floating through its interior. And this cavity is not alone. It sits in a neighborhood of other superbubbles, other cavities, other scars left by other chains of dying stars. The interstellar medium around us is not smooth, not uniform, and not empty. It is structured, layered, and architecturally complex in ways that most people have never imagined. The local bubble has neighbors, and its relationship with those neighbors reveals a galaxy that is far more violently sculpted than the calm night sky suggests. If the local bubble were the only cavity of its kind, it would already be extraordinary. 1,000 light-year wound in the interstellar medium, carved by 15 dead stars, still expanding after 14 million years, with every nearby star-forming region arranged on its walls. That alone would be enough to reshape how we think about the space around our solar system. But the local bubble is not alone. It is not even unusual. It is one cell in a vast, interlocking network of supernova-blown cavities that riddles the interstellar medium of the Milky Way. In every direction beyond the bubble's walls, other cavities press against it, overlap with it, and connect to it through narrow passages. The interstellar medium is not a smooth, uniform ocean of gas. It is foam, a frothy, scarred, three-dimensional lattice of bubbles and shells and compressed walls, all generated by the same process that created our own cavity. Massive stars living fast, dying violently, and reshaping the gas around them on scales of hundreds of light years. Understanding the local bubble in isolation is like studying a single apartment without realizing it sits inside a building, on a block, in a city. The apartment is real, its walls are real, but its shape, its position, and its very existence are determined by the larger architecture surrounding it. To grasp what the local bubble truly is, you have to see what presses against it from the outside. The most important neighbor is the Loop 1 superbubble. It is larger than the local bubble, more energetic, and far more violent, and it sits immediately adjacent to us in the direction of the galactic center. Loop 1 was created by the same stellar association responsible for the local bubble, Scorpius-Centaurus. But while the local bubble was carved by the earlier generations of supernovae in that association, Loop 1 represents the work of more recent and ongoing stellar activity. The upper Scorpius subgroup, the youngest component of Scorpius-Centaurus, has been producing powerful stellar winds and supernova explosions that have inflated a second, larger cavity overlapping with and pressing against the local bubble from the direction of the constellations Scorpius and Ophiuchus. Loop 1 is named for its appearance in radio continuum observations, where it shows up as a vast arc of enhanced radio emissions sweeping across a huge swath of sky. The structure spans roughly 115 degrees as seen from Earth, making it one of the largest features visible in radio maps of the Milky Way. Its center lies in the direction of the Scorpius-Centaurus association, roughly 400 to 500 light-years away, though estimates of its precise distance and three-dimensional geometry have varied significantly across different studies. Some researchers have placed portions of Loop 1 as close as 150 parsecs from the Sun. Others have argued that certain features attributed to Loop 1 actually originate much farther away, possibly even near the galactic center. What is not disputed is that Loop 1 and the local bubble are interacting. The boundary between the two cavities is not a clean wall. It is a disturbed, compressed zone, where the expanding shells of both superbubbles have collided and merged. Observations with the ROSAT X-ray satellite in the 1990s revealed direct evidence of this interaction shell, a region of enhanced X-ray emission lying between the two cavities, consistent with hot gas compressed at the interface where two expanding shockwaves met. This collision zone sits roughly 230 to 400 light-years from the Sun in the direction of Scorpius-Centaurus, depending on the line of sight. It is not a distant abstraction. In some directions, it is closer than many of the well-known stars visible to the naked eye on a dark night. It is not a distant abstraction. It is close, closer than many of the stars visible to the naked eye on a dark night. The boundary between our superbubble and the one next door is practically in our backyard, and the interaction has consequences. The collision between the two expanding shells compressed the gas at the interface, creating conditions that may have given rise to the very cloudlets drifting through our bubble's interior. The cluster of local interstellar clouds, the family of warm, partially ionized gas wisps that includes the local interstellar cloud currently surrounding our solar system, has long been suspected of originating at or near this interaction zone. The bulk motion of these cloudlets points back toward the Scorpius-Centaurus region, consistent with material squeezed out of the collision boundary and flowing inward through the local bubble's interior. If this interpretation is correct, then the thin wisp of interstellar gas that our solar system is currently passing through, the cloud whose particles Voyager 1 and Voyager 2 encountered when they crossed the heliopause, is itself a product of the collision between two superbubbles. The gas touching our heliosphere right now was shaped by the same large-scale interstellar violence that carved the cavity we live in. Even at the smallest scales, the architecture of the bubble and its neighbours reaches down to affect our immediate environment. But the connection between the local bubble and Loop 1 goes beyond a simple collision boundary. The two cavities appear to be linked by at least one narrow passage, a structure astronomers call the Lupus Tunnel. This tunnel is a corridor of low-density gas that threads through the compressed wall separating the two superbubbles, creating a physical channel through which material and energy can flow between them. The Lupus Tunnel was identified through observations of interstellar absorption towards stars in the direction of the constellation Lupus. Stars along certain lines of sight showed anomalously low absorption, indicating that the gas between us and those stars was thinner than the surrounding shell material. The pattern was consistent with a narrow opening in the wall, a tube of relatively empty space connecting the interior of the local bubble to the interior of Loop 1. This tunnel is not unique. Theoretical models of the interstellar medium have long predicted that superbubbles should be connected by such passages. When two expanding cavities grow close enough, their shells thin at the point of nearest approach, and eventually the walls can rupture, creating tunnels that link the interiors. The result is a network of interconnected cavities, a plumbing system of hot, low-density gas threaded through the denser interstellar medium. The local bubble shows evidence of multiple such connections. In addition to the Lupus Tunnel linking it to Loop 1, there are candidate tunnels in the direction of the constellation Canis Major, where a long, narrow extension of low-density gas stretches roughly 200 parsecs outward from the bubble. Another possible connection extends toward the Gum Nebula, a large emission nebula roughly 1,300 light-years away in the direction of Vela and Puppis. And the 2024 chimney model of the bubble suggests that the open northern cap of the structure itself functions as a tunnel of sorts, venting material directly into the Milky Way's lower halo. The picture that emerges is not of an isolated cavity floating in a uniform medium. It is of a single chamber in an interconnected network of chambers, linked by passages, pressed against by neighbors, and embedded in a galactic-scale architecture of hot gas and compressed shells. On the opposite side of the local bubble from Loop 1, another neighboring structure presses against the wall. The Pertau shell is a smaller, younger cavity located between the Perseus and Taurus molecular clouds, roughly 500 light-years from the Sun. It was identified in three-dimensional dust maps in 2021, and subsequent analysis revealed that it sits directly adjacent to the local bubble, with its wall in physical contact with our bubble's shell. The intersection of these two structures is not gentle. Where the Pertau shell meets the local bubble, the combined compression of their overlapping walls has created an unusually dense region of gas and dust. Researchers have proposed that this compression zone may have triggered star formation in the Taurus molecular cloud, one of the closest and most intensively studied stellar nurseries in the sky. If this is correct, then the stars being born in Taurus are not just sitting on the surface of the local bubble, they are being squeezed into existence at the collision point between two neighboring superbubbles. This is the kind of detail that transforms how you think about the space around the solar system. The star-forming regions near us are not independent objects that happen to form nearby. They are consequences of an architectural process, compressed into existence at the boundaries and intersections of enormous cavities blown open by ancient stellar explosions. The geography of nearby star formation is not random, it is structural, and the structures go far beyond the local bubble's immediate neighbours. In 2020, a team of astronomers led by João Alves announced the discovery of the Radcliffe Wave, a coherent, wave-shaped chain of dense gas clouds, stretching approximately 9,000 light-years through the galaxy, undulating above and below the galactic plane like a slow-motion ripple frozen in interstellar material. The Radcliffe Wave passes within roughly 1,000 light-years of the Sun, and includes some of the most prominent star-forming regions visible from Earth, including the Orion Nebula Complex, the Cepheus star-forming region, the North America Nebula, and Cygnus X. The Radcliffe Wave was invisible until three-dimensional dust mapping made it detectable. In two-dimensional projections on the sky, its component clouds appeared to be separate, unrelated objects scattered across different constellations. Only when their true three-dimensional positions were measured using Gaia data did the wave-like pattern emerge. The clouds are not random. They are arranged in a sinusoidal chain, rising and falling relative to the galactic midplane with a wavelength of roughly 2 kiloparsecs and an amplitude of roughly 160 parsecs. In 2024, further analysis confirmed that the Radcliffe Wave is not just a static shape, it is oscillating. The gas clouds and young stellar clusters associated with the wave are moving vertically, bobbing up and down through the galactic plane in a pattern consistent with a traveling wave driven by the gravitational potential of the Milky Way's disk. The wave is alive, it is in motion, and it sits right next door to the local bubble. The scale of the Radcliffe Wave alone demands attention. At approximately 9,000 light-years in length, it is one of the largest coherent structures ever identified in the Milky Way's interstellar medium. It dwarfs the local bubble by nearly an order of magnitude. If the bubble is a room, the Radcliffe Wave is the entire street outside. It stretches across a significant fraction of the local spiral arm, threading through the galactic disk like a spine of dense gas and dust, connecting some of the most prominent star-forming regions visible from Earth. The wave's sinusoidal shape was invisible until three-dimensional mapping revealed it. In two-dimensional projections on the sky, the molecular clouds that make up the wave appear as unrelated objects scattered across different constellations, Orion in one part of the sky, Cepheus in another, Cygnus in yet another. There was no reason to suspect they were connected. But when Gaia data allowed researchers to measure the true three-dimensional positions of these clouds, the pattern snapped into focus. The clouds are not scattered randomly. They are arranged in a wave, rising and falling relative to the galactic midplane with a remarkably regular pattern. The wavelength of the oscillation is roughly 6,500 light-years. The amplitude, the height of the peaks above and below the midplane, reaches approximately 520 light-years at its maximum. The Sun sits close to one of the wave's crests, within roughly 1,000 light-years of its nearest segment. The 2024 kinematic study added a crucial dimension to this discovery. Using line-of-sight velocity measurements of carbon monoxide gas and three-dimensional velocity data for young stellar clusters embedded in the wave, researchers demonstrated that the wave is not a frozen structure. The clouds are moving vertically, oscillating up and down through the galactic plane in a pattern consistent with a traveling wave. The most massive star-forming regions associated with the wave, including the Orion Complex, the Cepheus Clouds, the North American Nebula region, and Cygnus X, are all participating in this coherent vertical motion. The physical mechanism driving the oscillation appears to be the gravitational restoring force of the galactic disk itself. When a mass of gas rises above the midplane, the gravitational pull of the disk's stars, gas, and dark matter pulls it back down. It overshoots, drops below the midplane, and is pulled back up again. This creates a natural oscillation whose period depends on the local density of the galactic disk. By measuring the oscillation of the Radcliffe wave, researchers were able to independently constrain the local gravitational potential of the Milky Way and estimate the Sun's own vertical oscillation period through the galactic plane, arriving at a value of roughly 95 million years, somewhat longer than traditional estimates that clustered around 60 to 70 million years. The discovery that the Radcliffe wave oscillates transformed it from a curiosity of interstellar cartography into a dynamical probe of galactic structure. A 9,000 light-year chain of molecular clouds, bobbing coherently through the galactic plane, is not just a feature of the local interstellar medium, it is a seismograph. Its motion encodes information about the mass distribution of the Milky Way's disk in the solar neighborhood, information that is otherwise extremely difficult to obtain. But the Radcliffe wave is relevant to the local bubble story for a more specific reason. The wave's proximity and its connection to the star-forming history of the solar neighborhood raise the possibility that the two structures are not merely adjacent, but causally linked. The supernovae that carved the local bubble originated in the Scorpius-Centaurus association. Those stars had to form somewhere. They did not appear spontaneously in the middle of empty space. They condensed out of a molecular cloud, which itself was part of a larger structure in the interstellar medium. The 2024 kinematic analysis noted that the Radcliffe wave is drifting radially outward from the galactic center and suggested that the stellar cluster whose supernovae ultimately created the local bubble may have been born within the wave's gas before migrating to the position where the explosions occurred. If this connection is real, then the causal chain extends even further back than the supernovae themselves. The Radcliffe wave, a 9,000 light-year oscillating chain of gas, gave birth to the stars whose deaths carved the 1,000 light-year cavity in which our solar system now drifts. The bubble is not just adjacent to the wave, it may be the wave's offspring. And the stars now forming on the bubble's surface, triggered by the compression of its expanding shell, represent the next generation in a chain of cause and effect stretching across thousands of light-years and tens of millions of years. The relationship between the Radcliffe wave and the local bubble is still being investigated, but the spatial arrangement is striking. The local bubble is embedded between two large-scale galactic features, the Radcliffe wave on one side and a structure called the split on the other. The split is a long, low-density channel in the interstellar medium that runs roughly parallel to the Radcliffe wave but on the opposite side of the bubble. Together, these two features bracket the local bubble, framing it within the larger architecture of the Milky Way's local spiral arm. Some researchers have proposed that the supernovae which carved the local bubble may have originated from stars born in the Radcliffe wave itself. The 2024 kinematic analysis of the wave suggested that the cluster whose deaths ultimately created the expanding local bubble may have been born within the wave's gas before drifting to the position where the explosions occurred. If this connection holds, the local bubble is not just adjacent to the Radcliffe wave, it is a product of it. The wave gave birth to the stars that died to create the cavity we inhabit. This nesting of cause and effect, structures giving rise to stars that create new structures that trigger new rounds of star formation, is not a peculiarity of our neighborhood. It is how the interstellar medium works everywhere in the galaxy. The Milky Way's disk is riddled with superbubbles at every scale, from small cavities a few dozen light-years across to enormous structures spanning 1,000 light-years or more. These bubbles overlap, collide, merge and interact, creating the complex foamy texture that characterizes the interstellar medium throughout the galactic disk. How pervasive is this foamy architecture? The numbers are striking. Within roughly 3,000 light-years of the Sun, astronomers have identified at least a dozen distinct superbubbles or large shell structures in addition to the local bubble itself. Loop 1, Loop 2, Loop 3, the Orion Eridanus superbubble, the Per-Tau shell, the Cepheus flare shell, the Gum Nebula, the shell catalogued as GSH 238 +00 +09, the Antlia supernova remnant, the Vela supernova remnant and its associated cavity, and several smaller or less well-defined structures. Each of these was produced by the same fundamental process: one or more massive stars reaching the end of their lives and injecting enormous amounts of energy into the surrounding interstellar medium. These structures are not distributed randomly. They cluster along the galactic plane, concentrated in the spiral arms and interarm regions where massive star formation is most active. They range in size from a few tens of parsecs for young, individual supernova remnants to several hundred parsecs for mature superbubbles inflated by multiple sequential explosions. Their ages span from less than 100,000 years for the youngest remnants to tens of millions of years for the oldest and most evolved cavities. At any given moment, the interstellar medium in the solar neighborhood contains superbubbles at every stage of their life cycle, from freshly blown cavities still radiating brightly in X-rays to ancient, faded structures whose walls have largely dispersed back into the ambient medium. The volume-filling fraction of hot, low-density gas in the galactic disk has been debated for decades. Early theoretical estimates, following the Cox-and-Smith model from 1974, suggested that supernova remnants should overlap frequently enough to fill 50 to 70% of the disk's volume with hot plasma. More recent observational estimates have generally been lower, in the range of 20 to 40%, depending on how the boundaries of individual cavities are defined and how the contribution of the warm ionized medium is accounted for. But even at the lower end of these estimates, a substantial fraction of the interstellar medium in the solar neighborhood consists of supernova-carved cavities rather than undisturbed ambient gas. The observational evidence for this foam-like structure comes from multiple independent techniques. Soft X-ray surveys, particularly those conducted by ROSAT in the 1990s and more recently by the eROSITA instrument, reveal diffuse X-ray emission from hot plasma filling the interiors of nearby superbubbles. Radio continuum maps at 408 MHz show the arc-shaped shells of expanding remnants silhouetted against the galactic background. Ultraviolet absorption spectroscopy, using space telescopes to observe the absorption lines imprinted on starlight by intervening gas, reveals the density, temperature, and velocity of interstellar material along thousands of individual lines of sight, building up a statistical picture of the medium's structure. And three-dimensional dust maps constructed from Gaia data now provide direct volumetric images of the shells, walls, and cavities in the solar neighborhood with parsecant scale resolution. When you combine all of these datasets, the picture is unambiguous. The interstellar medium within a few thousand light-years of the Sun is not a smooth, uniform ocean of gas. It is riddled with cavities. It is partitioned into cells. Its density varies by factors of 1,000 or more over distances of a few hundred light-years. Dense more. When you look at the Orion Nebula through a telescope, molecular clouds containing hundreds of thousands of solar masses sit embedded in the compressed walls between cavities, while the cavities themselves contain plasma so sparse that a volume the size of Earth might hold only a few thousand atoms. This is the environment in which our solar system is embedded. Not a void, not a uniform medium. A foam, a three-dimensional lattice of hot, low-density cavities, bounded by thin, dense walls, interconnected by tunnels, continuously reshaped by the ongoing cycle of stellar birth and explosive stellar death. The local bubble is one cell in this foam. Its neighbors are other cells. The walls between them are shared boundaries where the compressed remnants of ancient shockwaves meet, and the entire structure extends outward across the galactic disk in every direction, far beyond the reach of current three-dimensional mapping. The foam analogy is not casual, it is physically precise. Imagine filling a bathtub with soap bubbles. Each bubble has thin walls. The walls of adjacent bubbles press against each other, creating shared boundaries. Where three or more bubbles meet, the walls intersect in narrow ridges. The interior of each bubble is mostly empty. The material is concentrated in the walls and intersections. Now scale that image up by a factor of 100 billion, and you have the interstellar medium of the Milky Way. Supernova-blown cavities are the bubbles, the compressed gas and dust swept into their walls from the thin membranes. The molecular clouds and star-forming regions that develop in the compressed walls are the ridges where bubbles meet. The hot, sparse interiors of the cavities contain the low-density plasma that fills most of the volume, and the entire structure is dynamic, constantly evolving as old bubbles fade and new ones are blown open by the next generation of massive stellar deaths. This foam-like architecture was first predicted theoretically in the 1970s by the physicists Cox and Smith, who proposed that supernova remnants should overlap frequently enough to create a pervasive network of hot, low-density tunnels threading through the denser interstellar medium. Their model suggested that a significant fraction of the galactic disk's volume, perhaps 50 to 70%, should be filled with hot gas from overlapping supernova remnants. Observational evidence accumulated over the following decades largely supported this picture, though the precise volume-filling fraction remains debated. What is no longer debated is that the structure exists. Three-dimensional dust maps, X-ray surveys, radio continuum observations, and ultraviolet absorption studies all confirm that the interstellar medium in the solar neighborhood is not smooth. It is architectural. Cavities and shells dominate the local landscape. The local bubble, Loop 1, the Pertau shell, the Orion Eridanus superbubble, the Cepheus flare shell, the Gum Nebula, and the structure catalogued as GSH 238 plus 00 plus 09. These are all distinct cavities or shells within roughly 1,000 light-years of the Sun, each one carved by its own history of stellar violence, each one interacting with its neighbours. The Orion Eridanus superbubble deserves special mention because of its scale and proximity. This enormous cavity, inflated by the massive stars of the Orion OB1 association, stretches roughly 1,200 light-years across and lies in the direction of the constellations Orion and Eridanus. Its near edge approaches within a few hundred light-years of the local bubble, and its shell may be in physical contact with the bubble's walls in some directions. The famous Orion Nebula, one of the most photographed objects in the night sky, sits inside this neighbouring superbubble, embedded in the gas and dust that lines its interior surface. The Orion Eridanus superbubble was inflated by successive generations of massive stars in the Orion OB1 association, one of the richest concentrations of young, luminous stars in the solar neighbourhood. This association contains 4 distinct subgroups spanning a range of ages from roughly 12 million years old to less than 2 million years. The oldest subgroups produce stars that have already died as supernovae, injecting their energy into the surrounding medium and inflating the cavity over millions of years. The youngest subgroup, which includes the brilliant stars of the Trapezium cluster at the heart of the Orion Nebula, is still actively producing intense ultraviolet radiation and powerful stellar winds that continue to shape the cavity's interior. The result is an enormous elongated structure stretching roughly 1,200 light-years from end to end, filled with hot plasma that glows in X-ray wavelengths. Observations with the Rosat satellite detected diffuse soft X-ray emission filling the cavity's interior, consistent with gas heated to temperatures exceeding 1 million degrees by the cumulative energy of multiple supernova explosions and the relentless winds of the surviving massive stars. The cavity is not spherical. It is stretched in the direction perpendicular to the galactic plane, suggesting that, like the local bubble, it may be in the process of blowing out through the thin disk of the galaxy. The near edge of the Orion Eridanus superbubble approaches within roughly 500 light-years of the Sun in certain directions, bringing it into proximity with the local bubble's own shell. In some analyses, the two structures appear to be in direct contact, their walls overlapping or merging in the region between the constellations Eridanus and Orion. The compressed zone where the two cavities meet may represent yet another boundary where the collision of expanding shells has triggered star formation, similar to the interaction between the local bubble and the Pertau shell in the Taurus region. This means that when you step outside on a clear winter night and look toward the constellation Orion, you are not just looking at a familiar pattern of bright stars. You are looking at the near wall of a neighboring superbubble, the faint fuzzy glow visible to the naked eye in Orion's sword. The feature that telescopes reveal as the spectacular Orion Nebula is a luminous patch on the interior surface of that adjacent cavity, lit up by the young massive stars embedded within it. You have seen a superbubble wall with your own eyes. You simply did not know what you were looking at. The architecture of the interstellar medium is not hidden in distant, inaccessible regions of the galaxy. It is visible on any clear night to anyone who knows where to look and what they are seeing. When you look at the Orion Nebula through a telescope, you are not just looking at a pretty cloud of glowing gas. You are looking at the interior wall of an adjacent superbubble, illuminated by the young, massive stars that formed on its compressed surface. The structure you admire is a product of the same process that created the cavity you are sitting inside. The local bubble and the Orion-Eridanus superbubble are siblings, parallel consequences of the same galactic scale recycling of interstellar material through cycles of stellar birth, death, and explosive restructuring. This realization forces a fundamental shift in how we think about the space around the solar system. The night sky is not a window onto a uniform, featureless galaxy. It is a view from inside one cell of a vast foam, looking outward through the walls of our cavity at the interiors and walls of neighboring cavities. Every molecular cloud we observe, every star-forming region we study, every diffuse glow of interstellar emission we detect, sits within this architectural framework of overlapping superbubbles, compressed shells, and interconnecting tunnels. And the architecture is not static. It is evolving on timescales of millions of years. Bubbles expand, collide, and merge. Shells thicken, fragment, and collapse into new star-forming clouds. New stars form, live for a few million years, and die in explosions that blow open new cavities inside or adjacent to the old ones. The process is self-sustaining. Star formation creates the conditions for the next round of star formation, mediated by the expansion and collision of superbubble shells. The local bubble itself is a snapshot in this ongoing process. 14 million years ago, it did not exist. The region now occupied by its empty interior was filled with ordinary interstellar gas, probably threaded with smaller structures and older faded supernova remnants from even earlier episodes of stellar death. Then the first massive star in the Upper Centaurus Lupus subgroup reached the end of its life, and the chain reaction began. Explosion after explosion, over millions of years, the cavity inflated, the walls expanded, and the surrounding medium was reorganized. 14 million years from now, the bubble may have faded entirely, its walls dispersed, its interior refilled with ambient gas drifting in from the surrounding medium, or it may have been re-energized by new supernovae from the remaining massive stars in Scorpius Centaurus, extending its lifetime and expanding its reach. Either way, the architecture of the interstellar medium will continue to be shaped by the same process. Massive stars dying violently and reshaping the gas around them. The solar system has no permanent address in this landscape. Our sun orbits the galactic center once every approximately 230 million years, and its path carries it through different regions of the interstellar medium over time. 5 million years ago, we were outside the local bubble, moving through denser, cooler interstellar gas. Today, we are near its center. In another 10 or 20 million years, we may have drifted out the other side, entering a different cavity or passing through a compressed shell into an entirely new interstellar environment. Our current position inside the local bubble is temporary, a brief chapter in the Sun's 4.5 billion year journey around the galaxy. But it is not insignificant. The environment inside the bubble, with its low gas density, high plasma temperature, and relatively sparse dust, affects the heliosphere, the flux of cosmic rays reaching Earth, and possibly even the conditions for life on our planet's surface. Some researchers have speculated that the interstellar environment experienced by the solar system over geological time may have influenced climate, atmospheric chemistry, and biological evolution, though these connections remain speculative and difficult to quantify. What is not speculative is the structure itself. The local bubble is real. Its neighbours are real. The tunnels connecting them are real. The compressed walls producing new stars are real. The foam-like architecture of the interstellar medium, with its overlapping cavities and shared boundaries, is real. And all of it was invisible to human understanding until the last few decades of careful observation, three-dimensional mapping, and computational reconstruction. We spent centuries staring at the night sky without realizing we were looking at it from inside a specific structure. We catalogued molecular clouds without knowing they were all fragments of the same expanding shell. We studied nearby star-forming regions without recognizing they were products of a single coherent process. We mapped the interstellar medium without seeing the foam. Now we see it. And what it reveals is a galaxy that is not passively sitting in equilibrium, but actively, violently restructuring itself at every scale, in every direction, at every moment. The space around the solar system is not empty. It is not neutral. It is not calm. It is a scarred, architecturally complex, dynamically evolving environment shaped by millions of years of explosive stellar death. And we are embedded in it, not observing it from outside, not floating above it, inside it, one tiny planetary system, drifting through one cell of a galaxy-wide foam, surrounded on every side by the compressed remnants of ancient violence. The question that remains is not what the local bubble looks like, or how it formed, or what sits next to it. We know those answers now, at least in broad outline. The question that remains is harder, and it reaches beyond astronomy into something more unsettling. What does it mean to live inside a structure you cannot see? Here is something that should unsettle you. The local bubble is roughly 1,000 light-years across. It surrounds our solar system in every direction. Its walls are made of compressed gas and dust piled up by the shockwaves of approximately 15 dead stars. Nearly every star-forming region within 500 light-years sits on its surface. It has been mapped in 3 dimensions. Its expansion rate has been measured. Its origin has been reconstructed down to individual supernova events confirmed by isotopic evidence preserved in Earth's ocean sediments. It is one of the most thoroughly documented large-scale structures in the nearby galaxy, and yet no human being has ever seen it. Not with their eyes, not from the ground, not from orbit, not from the surface of any world. The local bubble is completely invisible to direct human perception. You cannot look up at the night sky and point to it. You cannot photograph it. You cannot detect its presence through any sensation available to an unaided human observer standing on the surface of the Earth. It surrounds you on every side, shapes the interstellar environment in which your solar system is immersed, determines where the nearest star-forming regions are located, and influences the cosmic ray flux passing through your atmosphere at this very moment. And it is entirely hidden from view. This is not because the bubble is faint or distant or obscured. It is because you are inside it. And the fundamental problem with being inside a structure is that the structure becomes the background. It becomes the default. It becomes the thing you do not notice because you have never experienced anything else. Every star you have ever seen is inside the local bubble. Every constellation you have ever learned to recognize is composed of stars within the bubble's interior. The night sky you grew up with, the sky that every human civilization in history has used to navigate, to tell stories, to mark seasons and build calendars, is a view from inside this cavity. You have never seen the sky from outside the bubble. No human ever has. No human alive today ever will. This means that everything you think of as the normal appearance of the night sky is in fact the appearance of the sky from inside a specific interstellar environment. The density of visible stars, the brightness of the Milky Way band, the relative darkness between star clusters, and the apparent distribution of nebulae, all of these features are shaped by the fact that you are looking through the bubble's sparse interior, rather than through the denser interstellar medium that exists beyond its walls. If the solar system were located outside the bubble, embedded in a region of average interstellar density, the night sky would look different. More dust would dim the light of distant stars. Certain wavelengths would be absorbed more heavily. The Milky Way band might appear brighter or more structured in some directions and darker in others. You have never seen that sky. You do not know what normal looks like. You know only what the sky looks like from inside this particular scar. This is not a trivial observation. It strikes at one of the deepest assumptions in the history of astronomy. The idea that our location in the universe is not special. The Copernican principle, the philosophical foundation of modern cosmology, holds that Earth does not occupy a privileged or unusual position. We are not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. At every scale, science has systematically removed humanity from positions of cosmic importance. The local bubble does not exactly violate this principle, but it complicates it in a way that most discussions of cosmic mediocrity ignore. Our location is not special in the sense of being chosen or designed. The Sun drifted into the local bubble 5 million years ago by the ordinary mechanics of its galactic orbit. There is nothing purposeful about our position, but our location is unusual in a purely statistical sense. The interior of a superbubble is a low-density environment that occupies a significant but not dominant fraction of the galactic disk's volume. Not every star in the Milky Way sits inside a superbubble. Many stars are embedded in denser regions of the interstellar medium, inside spiral arms, near molecular clouds, in the compressed walls between cavities. Our Sun happens to be passing through the interior of a large, recently formed superbubble, and that passage affects what we observe and how we interpret it. This is not the same as saying we are at the center of the universe, but it is a reminder that our observational vantage point is not neutral. We are not looking at the galaxy from a blank, featureless location. We are looking at it from inside a structure, and that structure filters, frames, and shapes what we see. Consider what this means for the history of astronomy itself. For most of human history, the interstellar medium was completely unknown. Astronomers studied stars, planets, comets, and nebulae. The space between the stars was assumed to be empty. The very concept of interstellar gas and dust did not gain wide acceptance until the early 20th century, when observations of reddening and dimming of starlight revealed that space was not perfectly transparent. The interstellar medium was discovered not by seeing it directly, but by noticing its effects on the light passing through it. The local bubble was suspected even later, in the 1970s, through the indirect evidence of soft X-ray emissions and anomalously low interstellar absorption toward nearby stars. Its three-dimensional structure was not reconstructed until the 2020s. For the vast majority of the history of astronomy, from the ancient Greeks through Copernicus, through Galileo, through Newton, through Einstein, nobody knew we were inside a cavity. Every observation made, every model constructed, every theory proposed, was formulated without any awareness that the observer was embedded in a specific, physically real interstellar structure. This does not mean those observations and theories were wrong. General relativity does not depend on whether the Sun sits inside a superbubble. The laws of stellar evolution are the same regardless of local interstellar conditions. But certain measurements, particularly those sensitive to the local interstellar environment, were made without accounting for the bubble's influence. Early estimates of the soft X-ray background, for example, were initially interpreted as evidence of a uniformly hot interstellar medium pervading the galaxy. It took decades to realize that much of the observed X-ray emission was coming from the hot gas inside the local bubble itself, a local phenomenon masquerading as a universal one. This pattern, local conditions being mistaken for universal truths, is one of the oldest traps in science, and the local bubble is a reminder that even modern astronomy is not immune to it. We observe the universe from inside a structure. That structure affects our observations, and the effects are subtle enough that they can go undetected for decades. The deeper lesson is about the nature of embeddedness itself. Human beings are embedded creatures. We live inside systems that we cannot step outside of to examine objectively. We are embedded in our planet's biosphere, in our species' evolutionary history, in our culture's assumptions, in our brain's perceptual architecture. At every level, the medium we exist within shapes what we can perceive and what we cannot. The local bubble is simply the interstellar version of this universal condition, and it is not only a matter of perception. The bubble has physical consequences for the solar system. The density of the interstellar medium surrounding the heliosphere determines how large and how effective the heliosphere is as a shield against galactic cosmic rays. Inside the local bubble, where the interstellar medium is extremely sparse, the heliosphere can expand to a relatively large size. The solar wind pushes outward against minimal resistance, inflating a protective cocoon that deflects a significant fraction of incoming cosmic rays before they reach the inner solar system. If the solar system were located outside the bubble, embedded in a region of higher interstellar density, the heliosphere would be compressed. The denser surrounding medium would push inward against the solar wind, shrinking the heliosphere and allowing more cosmic rays to penetrate to the orbits of the inner planets. The cosmic ray flux at Earth's surface would increase. The effects on atmospheric chemistry, cloud formation, and radiation exposure are not fully understood, but they are not zero. Some researchers have proposed that the interstellar environment experienced by the solar system over geological time has influenced Earth's climate and biological evolution, though these connections remain difficult to quantify with precision. What is clear is that the local bubble is not merely a backdrop. It is an active participant in the conditions that prevail in our planetary neighborhood. The environment we call home is not just the solar system. It extends outward through the heliosphere, through the local interstellar cloud, and into the bubble's sparse interior. These layers are nested, interconnected, and mutually dependent. Change the outer layer, and the inner layers respond. The geological record offers tantalizing hints that such changes have occurred in Earth's past. The solar system has been orbiting the galactic center for 4.5 billion years, and during that time it has passed through a wide variety of interstellar environments. It has transited spiral arms, crossed regions of higher and lower gas density, and likely passed through or near other superbubbles, molecular cloud complexes, and compressed shell structures. Each transition would have altered the size and effectiveness of the heliosphere. When the Sun passes through a region of denser interstellar gas, the increased external pressure compresses the heliosphere inward. In extreme cases, the heliopause could be pushed inside the orbit of Pluto, or even closer. With the heliosphere contracted, the flux of galactic cosmic rays reaching Earth's atmosphere would increase significantly. These high-energy particles interact with atmospheric molecules, producing cascades of secondary particles that reach the surface. At elevated levels, cosmic rays can affect atmospheric chemistry, influencing the production of isotopes like beryllium-10 and carbon-14, and potentially affecting cloud nucleation processes that influence climate. Some researchers have proposed correlations between the solar system's passage through galactic spiral arms and periods of increased glaciation or biological disruption recorded in Earth's geological and fossil records. These correlations remain controversial and difficult to disentangle from the many other factors that influence climate and evolution over hundreds of millions of years. But the physical mechanism is sound. A denser interstellar environment compresses the heliosphere, increases cosmic ray flux, and alters the radiation environment at Earth's surface. The question is not whether the effect exists, but how large it is, and whether it has been significant enough to leave detectable traces in the geological record. What is less speculative is what would happen if the solar system were to exit the local bubble entirely. Outside the bubble, the interstellar medium returns to something closer to average galactic density, roughly 100 times denser than the sparse plasma currently surrounding the heliosphere. The transition from the bubble's interior to the denser medium beyond its walls would compress the heliosphere dramatically. The cosmic ray flux at Earth could increase by a measurable factor, and the interstellar gas pressing against the outer solar system would change in temperature, composition, and velocity. The Sun will not exit the local bubble anytime soon. At current estimates of the bubble's size and the Sun's trajectory through the galaxy, we are likely to remain inside the cavity for at least several million more years, possibly longer. But the transition is inevitable on astronomical timescales. At some point in the distant future, the solar system will leave this protected environment and enter a denser, less hospitable region of interstellar space. When it does, the conditions at Earth's surface will change in ways that depend on the density and temperature of whatever interstellar environment we encounter next. This interconnection is part of what makes the local bubble so conceptually challenging. It is too large to see, too slow to watch, and too pervasive to escape. Its effects are real but diffuse, spread across scales of hundreds of light years and timescales of millions of years. It operates in a domain that lies entirely outside the range of human intuition. Too big for the senses, too slow for a lifetime, too quiet for drama. And yet it is the actual environment in which our solar system exists. There is an analogy that helps. Though, like all analogies for cosmic structures, it eventually breaks down. Imagine an ant crawling along the inner surface of an enormous balloon. The balloon is so large that its curvature is imperceptible to the ant. The ant cannot see the balloon's surface curving away in the distance. It cannot detect the balloon's edges. It has no way to perceive the shape of the structure it is crawling on, because every direction it looks appears flat. The balloon's surface is the ant's entire world, and because the ant has never experienced anything else, it has no reason to suspect that a larger structure exists. Now imagine telling the ant that it lives on the inside surface of a vast curved enclosure created by an ancient explosive event. The ant would have no framework for understanding this information. Its perceptual world is too small, its lifespan too short, its sensory apparatus too limited to grasp the shape of the thing it inhabits. Humans face an equivalent limitation with the local bubble. We crawl along the inside of a 1,000 light-year cavity without any sensory awareness that the cavity exists. We needed centuries of technological development, including space telescopes, X-ray observatories, radio surveys, spectroscopic analysis, isotope geochemistry, and billion-star astrometric catalogues, just to detect the structure. And even now, with all of those tools, the bubble remains an abstraction for most people. A diagram in a research paper, a visualization in a press release, not a felt reality. But it is real. The walls are real. The hot gas is real. The compressed shell producing new stars is real. The tunnels to neighboring superbubbles are real. The chimney venting material into the galactic halo is real. The iron 60 atoms that settled on the ocean floor 2 million years ago after drifting across interstellar space from a dying star are real. The local bubble is as real as the ground you stand on. You simply cannot see it because you are inside it, and it is far too large for human senses to resolve. This is the deepest challenge the local bubble poses. Not a scientific challenge, though plenty of scientific questions remain about its detailed structure, its precise history, and its interactions with neighboring cavities. The deepest challenge is conceptual. It is the challenge of accepting that the space you call local is already vast, already structured, already shaped by events that occurred millions of years before your species existed. It is the challenge of understanding that even your immediate cosmic neighborhood, the region you might casually think of as nearby space, is a complex, historically determined environment with architecture, boundaries, origins, and a future that will unfold long after your sun has exhausted its fuel. Most people, when they think about the scale of the universe, jump immediately to the largest structures. They think about the observable universe, 93 billion light-years across. They think about galaxy clusters, superclusters, the cosmic web. They imagine the solar system as a tiny dot lost in an incomprehensibly vast cosmos. And that picture is correct, as far as it goes. But it skips a step. It leaps from the solar system to the galaxy without pausing to notice that the space between those two scales is already enormous, already structured, and already far more complex than the empty void most people imagine. The local bubble occupies that overlooked middle ground. It is not the solar system, and it is not the galaxy. It is the environment between those scales, the actual physical surroundings in which our planetary system is immersed. And it is roughly 1,000 light-years across. That distance is already staggering. Light takes a millennium to cross it. The fastest spacecraft ever built would need tens of millions of years. The entire solar system, including the outermost reaches of the Oort cloud, fits inside the bubble with room to spare by a factor of several hundred. This is what local means when you use the word honestly at interstellar scales. Local does not mean small. Local does not mean simple. Local does not mean empty. Local means a 1,000 light-year cavity carved by 15 supernovae, bounded by walls of compressed gas and dust, connected to adjacent superbubbles by tunnels, flanked by the oscillating Radcliffe wave, venting material through a chimney into the Milky Way's halo, and still expanding outward at roughly 7 kilometers per second after 14 million years. That is your neighborhood. Not the few light years between the Sun and Alpha Centauri. Not the handful of nearby stars visible on a dark night. The neighborhood is the bubble. And the bubble is already part of a larger network of interconnected cavities, which is itself embedded in the spiral arm structure of the galactic disk, which is itself one component of a galaxy containing 400 billion stars. Each layer is larger than the one before. Each layer was invisible until technology revealed it. And at every layer, the structure is not smooth and featureless, but scarred, architectural, and historically shaped by violence. There is a tendency, when confronting scales this large, to retreat into abstraction. The numbers become meaningless. The distances become incomprehensible. The structures become diagrams rather than realities. This retreat is understandable. Human brains did not evolve to process information at these scales. Our perceptual systems are calibrated for the distances and timescales relevant to survival on the African savanna. A few miles of terrain, a few decades of lived experience. Nothing in our evolutionary history prepared us to feel the reality of a 1,000 light-year cavity. But the cavity does not need you to feel it in order to be real. It surrounds you regardless of whether you comprehend it. It shaped the star-forming regions that produce the heavy elements in your body, regardless of whether you know their names. It influences the cosmic ray flux reaching your atmosphere, regardless of whether you have ever heard the term heliosphere. The local bubble is not a concept that requires your awareness to function. It is the environment. It operates whether you notice it or not. And this, finally, is what separates the local bubble from the usual catalogue of cosmic superlatives. Most discussions of cosmic scale aim for awe. They want you to feel small. They want you to marvel at the size of the universe and experience a pleasurable vertigo at your own insignificance. The local bubble does something different. It does not make you feel small in the abstract. It makes you feel embedded in the specific. It does not point to a distant, incomprehensible vastness and say, look how big that is. It points to the space immediately surrounding your solar system and says, this is already structured. This is already enormous. This is already shaped by a history you never knew about. The shock of the local bubble is not that the universe is big. Everyone knows the universe is big. The shock is that even the part of the universe you thought you understood, the nearby part, the local part, the familiar night sky full of recognizable constellations, is already part of a much larger surrounding environment shaped by ancient violence and large-scale interstellar architecture. You did not need to travel to the edge of the observable universe to find structure beyond your comprehension. You only needed to look at the space you were already sitting in. The stars forming right now on the bubble's surface, hundreds of light years from where you sit, are being born because the same explosions that emptied the space around your sun compressed the gas at the edges into dense enough clouds for gravity to take hold. You are not separate from that process. You are downstream of it. The heavy elements in your body were forged in earlier generations of stars, scattered by earlier supernovae, cycled through the interstellar medium, and eventually incorporated into the molecular cloud that collapsed to form the Sun and its planets 4.5 billion years ago. You are made of material that was processed by the same galactic machinery that carved the local bubble, just in an earlier cycle. You are a fish born in a current that has been flowing for 14 million years, in an ocean of currents that has been flowing for billions. You did not choose the current. You did not create it. You cannot see its edges, but it carries you, and it shaped the conditions that allowed you to exist. The local bubble is not a curiosity. It is not a footnote in a textbook about interstellar gas. It is the answer to a question most people never think to ask. What is the actual physical environment surrounding the solar system? Not the gravitational environment within the planetary orbits, not the stellar environment of the nearest few stars, the interstellar environment, the medium between the stars, the gas, the dust, the plasma, the magnetic fields, the density structures, the remnants of ancient explosions. The answer is a cavity, a scar, a chimney, a cell in a foam, a structure 1,000 light-years across, 14 million years old, still expanding, still producing new stars on its walls, still venting material into the galactic halo, and still completely invisible to the unaided human eye. You are inside it right now. You have been inside it for 5 million years. You will remain inside it, or inside whatever it becomes, for millions of years more. And everything you have ever seen in the night sky, every star, every constellation, every faint smudge of nebulosity, has been seen from within this structure, through its sparse interior, framed by its compressed walls, shaped by its violent history. The true scale of the local bubble is not measured in light years, though it spans 1,000 of them. It is measured in the distance between what people imagine when they think about the space around the sun and what actually exists there. That distance, the gap between the imagined void and the real architecture, is the true scale of the bubble, and it is enormous. The space you call local is already a landscape. It already has geography. It already has history. And you are already inside it, looking out from the interior of an ancient explosion, surrounded on every side by the compressed remnants of stars that died before your species existed, embedded in a structure so large that it took humanity's most advanced instruments to detect it, and so close that you have never once in your life been outside it. That is the local bubble. That is where you live.